Consider the following: A or B, all ORed with C. Now that has an equivalence, which is this: A can be ORed with B or C. Now this is a fact. And what we can do, we can have a look at a truth table for three variables. So I'm going to write down here A, B and C as my three variables. And if I've got three variables, they can be in combination in terms of the ones and zeros that they can represent. And we can have 8 combinations because there are three variables and it's 2 to the power 3. 2 to the power of the number of variables we have. And obviously 2 to the 3 is 8. 2 times 2 times 2 is 8. Now a quick way to produce the 8 combinations is as follows. We simply write down 4 zeros in this column followed by 4 ones. In this column 2 zeros, 2 ones, 2 zeros, 2 ones, and the last column we put 0 1 0 1 0 1 0 1. So we can see there's an identifiable pattern there. Now I'm going to build up the truth table for the expressions above, and I'm going to do it one column at a time. That's pretty laborious this, but just hang in there and watch what we do. Well, the first thing I'm going to do, I'm going to produce the column for A or B. And we're going to have a look at each entry in turn. So here we can see we've got 0 or 0, which is a 0. We have a 0 or 0 again, which is a 0. Here we have a 0 or 1, which is a 1. We have the same combination here, 0 or 1, which is a 1. We have a 1 or 0, which is a 1. Same combination here, 1 or 0, which is a 1. And finally, we can see the last two here are both 1 or 1, so we get 2 ones there. Now what I'm going to do, I'm going to take the column I've just produced, which is the A or B, and I'm going to OR that with the C. So let's see what we get for this. So we have these two, which gives us 0 or 0, which is a 0. This one is 1 or 0, which is a 1. This one is 0 or 1, which is a 1. This is 2 ones. 1 or 1 gives us a 1. Here we have a 0 or 1, which gives us a 1. Here we have 1 or 1, which gives us a 1. And here we have 0 or 1, which gives us a 1. And here we have 1 or 1, which gives us a 1. Let's now have a look at what we get for this, B or C. Let's have a look at each in turn. I have a 0 or a 0, which is a 0. I have a 0 or 1, which is a 1. I have a 1 or 0, which is a 1. I have a 1 or 1, which is a 1. I have a 0 or 0, which is a 0. I have a 0 or 1, which is a 1. I have a 1 or 0, which is a 1. And I have a 1 or 1, which is a 1. Now I'm going to take A and I'm going to OR that with the column I've just produced, the B or C column. And let's see what we get for this. Let's go through each in turn. Of course, this is pretty laborious, but nevertheless, let's just do it. Here we can see I have a 0 or a 0, which is a 0. Here I can see I've got a 0 or a 1, which is a 1. Here I can see I've got a 0 or a 1, which is a 1. I have a 0 or a 1, which is a 1. I have a 1 or a 0, which is a 1. I have a 1 or a 1, which is a 1. I have a 1 or a 1, which is a 1. I have a 1 or a 1, which is a 1. Now this is represented by this column. This is represented by this column. Let's look at both columns. We can see they're identical. Consequently, it is correct, the statement we've made here. Let's have a look at this statement here. A or B or C. And let's produce a combinational logic circuit for this. Well, the first thing I can see is that I have an A and a B going into an OR gate. where that is A and that is B. And at this point, this will produce A or B, which we can put in brackets like that. Now, if I take that and I pass that now to the input of another OR gate, which takes C as its other input. Let's draw the OR gate here. What I get at this point now is A or B ORed with C. If I now take this expression, which is A or B or C, what we now can see is this, that I have A, B and C as my variables. Now I'm going to take the B and the C and I'm going to put those through an OR gate, and what that will give me here is B or C, and that together with the A is now going to go as the input to another OR gate, and that will give me here the A ORed with the B or C. Now these combinational logic circuits look slightly different, but they have the same logic functionality. And we can't go through every combination here, it would be extremely tedious. So I'm just going to choose one. I'm going to choose the case when they're all 0. So here I can have A as a 0, B as a 0, and we will know for an OR gate we'll get a 0 out here. And that 0 will then be the input to this gate. If I make the C a 0, then obviously there's a 0 going to this OR gate, and the output under those circumstances would be a 0. If I come down here now and I make all of these zeros, then obviously this A will come along to the input of this gate and be a 0. The output of this OR gate is a 0, which means the input to this OR gate is a 0, and we have an output of 0. Now what I'd like you to do is to prove that for all of the other combinations of A, B and C, and those combinations are shown here in the truth table. Now we can therefore prove, or maybe not formally prove, but prove to ourselves that if all of the combinations give us the same outputs, then again this is another reason why we can make this statement here, that these two are equivalent. And this is one of the associative laws. There is another one that's covered in the next video.